Right now, inside every atom of your body, trillions of neutrons are quietly ignoring one of the most reliable rules in physics. Left on its own, floating in empty space, a neutron will live for only about 15 minutes before it falls apart. It breaks into a proton, an electron, and a tiny ghostly particle called a neutrino, and then it is gone. That is not a rare accident. That is what neutrons do. And yet, the carbon in your bones, the oxygen in your lungs, the iron in your blood, every one of those atoms is packed with neutrons that have been sitting there, perfectly stable, for billions of years, older than the Earth itself. Same particle, same forces, same universe. So what happens the moment a neutron steps inside a nucleus that lets it cheat death almost forever? Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Also, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. The paradox we opened with is not a metaphor, and it is not a rounding error. It is a straight, measured fact, verified in laboratories over and over again for the past century. So the first thing we have to do is take that paradox very seriously and let it sit uncomfortably in the mind for a little while. Because if you think you understand it too quickly, you are almost certainly filling in the blank with the wrong answer. Here is the free neutron half of the picture, told plainly. Take a neutron, any neutron, and pull it out of whatever atom it was sitting inside. Set it down, alone, in empty space. No other particles nearby, no force fields pushing on it, just a single neutron drifting. Do this in the cleanest, most careful experiment human beings have ever built, and then start a stopwatch. What you will measure is a mean lifetime of about 880 seconds. That is roughly 14.5 minutes. In that time, more than half of a large batch of free neutrons will be gone. Not moved, gone. The particle that was there is no longer there. In its place, you will find 3 completely different particles that were not there before. That is what physicists actually see. This is not theory laid over data, this is data. Since the 1930s, when James Chadwick first identified the neutron, we have been getting better and better at trapping small numbers of them and watching them for as long as we can. The most careful measurements today give a number very close to 878 seconds, with error bars of only a second or two either way. Different techniques disagree slightly, which is its own famous puzzle in modern physics, but no one is arguing about the general size of the number. Free neutrons live minutes, not hours, not days, not years, minutes. Getting to that number was not easy. Neutrons are electrically neutral, which means they do not respond to electric fields the way charged particles do. You cannot simply put them in a magnetic bottle the way you would put a proton or an electron. Physicists had to invent extremely subtle traps, some of them using the gravitational pull of the Earth and gently curved magnetic surfaces to keep ultra-cold neutrons hovering just above a specially shaped bowl for as long as possible. Others used narrow, cold beams of neutrons flowing steadily through a detector, counting how many decayed inside a well-defined region of space. The two methods, called bottle experiments and beam experiments, still give slightly different values, differing by around 10 seconds, and figuring out which one is right is an active area of research. But whichever method you trust more, the answer is minutes, not milliseconds, and not centuries. It is worth pausing on how remarkable it is that we know this number at all, because the neutron was one of the very last of the ordinary building blocks of matter to be identified, and pinning down its lifetime was harder still. For the first 3 decades of the 20th century, physicists had a rough picture of the atom as a nucleus surrounded by electrons, but the nucleus itself was mysterious. Something had to account for the extra mass of atoms beyond what the protons alone could provide, and various patches were proposed, including the idea that the nucleus contained extra protons and electrons stuck together in some way. None of the patches worked cleanly. The problem was that no one had ever seen the neutral something that the accounting demanded. The answer arrived in 1932, when James Chadwick at the Cavendish Laboratory in Cambridge ran careful experiments involving beryllium bombarded with alpha particles. Others had already noticed that the beryllium spat out a strange, penetrating radiation that could knock protons out of hydrogen-containing materials, and had interpreted it as high-energy gamma rays. Chadwick did the arithmetic more carefully and showed that no gamma ray could possibly have enough energy to eject protons the way this radiation did. The only thing that could do the job was a neutral particle with roughly the same mass as a proton. He wrote up a short letter to the journal Nature that year, and within months, physics had a new fundamental particle. The neutron had arrived. Chadwick's neutron was, at first, only a piece of accounting. Its lifetime, if it had one, was not known. It took another 20+ years of increasingly clever experimental work before anyone could actually watch free neutrons decay in a laboratory in a controlled way, because you first had to figure out how to produce them in significant numbers, then figure out how to hold them or count them, then figure out how to detect the 3 particles that came flying out when one of them died. Each of those steps required its own generation of technology. Producing neutrons in significant numbers waited on the nuclear reactor, which arrived in the 1940s. Holding onto them long enough to watch them decay is a problem not fully solved even today. The 2 dominant modern techniques sit at the frontier of precision measurement, and the fact that they disagree by about 10 seconds in their measured neutron lifetime is one of the genuinely open puzzles in modern physics. The bottle experiments trap ultra-cold neutrons in a container, wait a while, and count how many are left. The beam experiments fire a steady stream of cold neutrons through a detector and count the decays they see per unit length of beam. In principle, both should give the same number. In practice, the bottle experiments consistently find a shorter lifetime than the beam experiments, by an amount that is small in absolute terms, but far larger than the error bars on either measurement. No one is sure why. Some physicists suspect an unknown decay channel in which a small fraction of neutrons decay into something other than a proton, electron, and antineutrino, perhaps into a dark matter particle of some kind, which would make the bottle experiments see too few surviving neutrons, while the beam experiments, which count only the standard decay products, see the correct rate for that specific channel. Others suspect subtle systematic errors in one or both types of experiment that have simply not been found yet. Either way, the disagreement is a live area of research, and settling it may or may not require new physics beyond the currently understood standard model. Even the detection of what actually comes out of a neutron decay is a piece of technical art. The proton left behind is easy enough to spot once you have the machinery for it. Protons are electrically charged and can be steered into detectors by magnetic fields, where they announce their arrival by a small electrical signal. The electron flying out is also charged and comparably easy to catch, and its energy can be measured with the same kinds of instruments used to study other charged particles. But the antineutrino is the one you cannot directly see at all. Antineutrinos pass through matter as if it were not there. A typical antineutrino can travel through a light year of solid lead without interacting even once. In practice, the antineutrino from a neutron decay is inferred, not detected. Physicists measure the proton and the electron, work out what fraction of the neutron's original energy and momentum they carry, and confirm that the missing balance is exactly what an antineutrino would have to carry away. The particle itself flies off into the void, unremarked, unseen, doing no further business with anything for very nearly forever. Now hold that fact next to the second one. The iron in a chunk of ordinary iron, the calcium in the shell of an egg, the nitrogen in the air you just breathed. Every one of those atoms contains at least one neutron, and in most cases, many neutrons. Those neutrons have been sitting there for as long as the atom has existed, which is often longer than the Earth itself. The nitrogen you just breathed was almost certainly forged inside a star that finished burning before our sun was born. Its neutrons are older than the ground under your feet. They have been quietly, patiently existing for billions of years, doing absolutely nothing that looks like decay. 2 facts, 1 particle. The gap between 14 minutes and 14 billion years is not something you can wave away. It is not that bound neutrons are decaying a little bit more slowly. It is that many of them do not decay at all, apparently ever, up to any limit anyone has been able to measure. The neutron in the carbon nucleus of a diamond, formed in the deep mantle of the Earth, is the same species of particle as the neutron floating alone in a beamline at a research reactor. The forces of nature do not have a special rulebook for one and a different rulebook for the other. And yet, the outcomes could not be more different. To understand why, we have to first understand what a free neutron is, where it comes from, and what it does. Then we have to understand exactly what it means for that neutron to decay. Only then will the second half of the story, the one about being bound inside a nucleus, actually make sense. So we start with the neutron alone. Free neutrons are not particularly common in everyday matter. Almost every neutron you will ever be near is safely tucked inside some atomic nucleus, glued in place by the strong nuclear force. To get a free neutron, you have to pry it loose from a nucleus. In practice, that means one of a few situations. Inside a working nuclear reactor, uranium atoms split and spray out fast neutrons. Cosmic rays smashing into the upper atmosphere knock neutrons loose from nitrogen and oxygen. Massive stars, during their final moments, produce oceans of free neutrons and use them to build heavier elements. Physicists build machines called spallation sources that fire high-energy protons at heavy metal targets and produce free neutrons on demand. In every one of these cases, whatever is producing the free neutrons is producing them because something violent has torn them out of the nuclei they were living in. Once loose, the free neutron does not last long by any human measure. But those minutes are enough for it to do a great deal of physics. A free neutron can be slowed down, cooled, bounced off surfaces, guided down long pipes, held in magnetic traps, and used to probe crystals and biological samples. Entire research fields are built on the assumption that you can generate free neutrons, work with them for a few seconds or minutes, and then let them expire. Their brief lifetime is not a bug in the experiments. It is a design constraint that everyone learns to work around. And it is genuinely brief. If you generate a free neutron and simply wait, the probability that it will still exist ticks down smoothly. After about 10 minutes, a bit less than half of the original neutrons in your batch have already decayed. After 30 minutes, only a small fraction remain. After an hour, essentially none. A free neutron is a walking clock, and its clock runs out very quickly compared to almost any other stable particle you can think of. Protons, as far as anyone has ever measured, live essentially forever. Electrons live forever. Photons live forever. The neutron is the odd one out among the everyday particles of matter. Alone, it cannot stay. To see why, we need to look inside a neutron. Because a neutron is not a fundamental particle in the way an electron is, zoom in far enough and you find that a neutron is a small, tightly packed bag of even smaller things. Specifically, A neutron is made of 3 quarks. 2 of them are a type called down quarks, and 1 is a type called an up quark. Bound tightly to those quarks is a swarming, glowing sea of particles called gluons, which are constantly popping in and out of existence and gluing everything together with the strong nuclear force. The whole assembly is about 1 femtometer across, which is 1 quadrillionth of a meter, and it holds together fantastically well as long as nothing disturbs it. The proton, its sibling, has almost exactly the same setup. 2 up quarks, 1 down quark, and the same gluon glue. So if you look at a proton and a neutron side by side, the only real internal difference is a single quark. The neutron has 1 extra down and 1 fewer up. Everything else is essentially the same. That tiny internal difference is where the whole story is going to live. That picture, quarks and gluons in a small volume, is important to get right. The quarks inside a neutron are not sitting still like beads on a string. They are moving at speeds close to the speed of light, exchanging gluons back and forth constantly, popping other quark-antiquark pairs into and out of existence around them, and generally behaving less like little marbles and more like a boiling foam of activity confined to a very small region. The neutron is not so much a solid object as a very small, very well-defined patch of the strong force having a permanent conversation with itself. All of that turbulence is what gives the neutron nearly all of its mass. If you added up just the bare masses of the 2 down quarks and the 1 up quark inside a neutron, you would get less than 2% of the neutron's total mass. The other 98% is energy. Kinetic energy of the quarks, energy stored in the gluon field, energy borrowed and repaid by virtual pairs. Mass, at this scale, really is just organized energy. Up and down quarks are not identical. They have slightly different masses, and they have different electric charges. An up quark carries plus 2/3 of the fundamental unit of electric charge. A down quark carries minus 1/3. If you add up the charges of 2 ups and a down, you get plus 1, which is why a proton is positively charged. If you add up the charges of 1 up and 2 downs, you get 0, which is why a neutron has no net charge and can wander through matter without being deflected by electric fields. That is exactly why free neutrons are so useful for probing materials, and also exactly why they are so much harder to detect than charged particles. Now here is the important thing. The down quark is slightly heavier than the up quark. Not by a lot. Not by any amount you would notice if you were building furniture, but by enough to matter when we are counting energies to 5 decimal places. Because the neutron has 1 more down quark than the proton, the neutron ends up being very slightly heavier than the proton. That is not a coincidence, and it is not a small detail. That tiny mass difference is exactly what powers the entire decay. Alright, we have the neutron. It is a little bag of 3 quarks and a mess of gluons, slightly heavier than its sibling the proton. Now let us watch what happens when a free one of these bags is left alone and its clock runs out. What does the actual decay look like? At some unpredictable moment, without any warning, one of the down quarks inside the neutron transforms. It does not fly out. It does not get knocked loose. It does not tunnel out of the bag. It simply changes. In the instant of the change, that down quark becomes an up quark. In the same instant, a brand new particle appears out of nowhere and then, essentially immediately, splits into 2 other brand new particles. The quark composition of the bag has now changed from 2 downs and an up to 1 down and 2 ups. That is no longer a neutron. It is a proton. The bag is still there, still holding together, still made of 3 quarks and gluons. But it now carries a net electric charge of plus 1. and it now has slightly less mass than the neutron did a moment ago. Where did the missing mass go? It went into the two brand new particles that appeared during the transformation. Those two particles are an electron, which flies away carrying negative electric charge and balancing the +1 on the proton so that no charge is created or destroyed overall, and an electron antineutrino, which is a nearly massless, electrically neutral, almost undetectable ghost of a particle that also flies away carrying some of the energy, and, importantly, carrying a property called lepton number that has to balance the ledger for reasons we will not fully get into here. Both the electron and the antineutrino zoom off in whatever directions the quantum accounting allows, sharing between them the leftover energy. So the summary is very clean. One neutron went in, one proton, one electron, and one electron antineutrino came out. Nothing was lost. Nothing was created from nothing. Every conserved quantity, electric charge, momentum, angular momentum, energy, lepton number, all of them balance perfectly on both sides. That is beta decay. Specifically, it is called beta minus decay because the electron flying out is negatively charged, and physicists in the early 20th century, before they knew what any of these particles actually were, gave the mysterious flying electron the name beta particle. The name stuck. Today, we know exactly what it is. It is an electron, born in the moment of decay, flying out of a nucleus or out of a free neutron because something else just changed identity. And the something else is a single quark. That is the piece that is easy to miss. It is very tempting to imagine the neutron as a proton with an electron somehow stuck to it, so that decay just means the electron pops off. That picture is wrong, and it was already known to be wrong more than 80 years ago. The electron does not exist inside the nutrient waiting to be released. Neither does the antineutrino. Both are created in the instant of the transformation. They are the results of a quark changing type, not passengers escaping from a container. This is where we have to introduce the force that makes any of this possible, because a quark cannot just decide to change type. It has to be persuaded to change by one of the fundamental interactions of nature, and only one interaction is capable of doing this particular thing. The strong force, which holds the quarks together, cannot change one quark type into another. The electromagnetic force cannot change one quark type into another. Gravity certainly cannot. The only force in nature that can turn a down quark into an up quark and produce an electron and an antineutrino in the process is the weak interaction. The weak interaction is the strangest of the four fundamental forces. It has almost no long-range presence. It does not hold matter together the way the strong force does. It does not push and pull the way electromagnetism does. Its main job in the everyday universe is to allow certain particles to change into other particles. It is the alchemist of the fundamental forces. And the thing it does most famously is exactly what we are watching here. Physically, the way the weak interaction reaches into a down quark and turns it into an up quark is by having the down quark briefly emit a heavy carrier particle called a W boson. Specifically, in this case, it emits a W- boson, which carries away 1 unit of negative electric charge, changing the quark from -1/3 to +2/3, and completing the transformation from down to up. The W- boson itself is enormously heavy compared to almost anything else at this scale. It is roughly 80 times heavier than the proton it will help produce. Under normal energy conditions, there is nowhere near enough energy sitting around to make a W boson from scratch. But quantum mechanics allows the W to exist as a virtual particle for an extremely short time before it has to disappear. In that fleeting existence, It flies just far enough to transform back into two lighter particles, an electron and an electron antineutrino, and vanishes. That is the mechanism. A down quark spits out a virtual W- for an unimaginably short moment. The W-, unable to hang around because it is far too massive to exist openly with the energy budget available, promptly falls apart into an electron and an antineutrino. Meanwhile, the down quark, having lost a unit of negative charge, is now an up quark. The neutron, which used to be a bag of two downs and an up, is now a bag of two ups and a down. It is a proton. The whole thing happened faster than anyone can measure, mediated by a particle heavy enough to be worthy of its own headlines when it was finally detected in the 1980s. When the W boson was finally directly produced and detected at CERN in 1983, in an experiment led by Carlo Rubbia and Simon van der Meer, it earned its discoverers a Nobel Prize the following year. What they saw fit the predictions of the weak interaction theory that had been assembled painstakingly over the previous 2 decades. The W had exactly the mass it was supposed to have, roughly 80 times heavier than a proton. It appeared exactly as often as theory predicted when the right kinds of collisions were staged. And it decayed, when it decayed, into exactly the kinds of particles it was supposed to produce, including electron-antineutrino pairs of the same character as those that come flying out of a decaying neutron. All of that confirms something that had been strongly suspected, but only indirectly measured. The rare virtual W bosons that live and die inside decaying neutrons are the same objects as the ones smashed briefly into real existence in the world's highest energy laboratories. Because the W boson is so heavy and so short-lived, the weak interaction at everyday energies has to work through what is essentially a keyhole. Only rarely can the quantum bookkeeping allow the W to briefly exist. That is why the weak interaction is called weak. It is not that the force itself is intrinsically feeble at close range. It is that the mediator is so heavy that borrowing enough energy to produce one, even virtually, is a very unlikely event per unit time. That unlikelihood, that reluctance of the quantum world to spontaneously produce a virtual W boson, is exactly why the free neutron survives for minutes instead of nanoseconds. On the timescale of the strong force, minutes are eons. If any force other than the weak one could drive this decay, the free neutron would fall apart almost the moment you created it. It survives as long as it does because it is waiting for a very unlikely thing to happen. And eventually, statistically, it does. There is one crucial idea we need to nail down before moving on, because if we get this wrong, everything in the next stretch will feel like a magic trick. The idea is this. The neutron does not decay because it is worn out. It does not decay because something inside it wears down and eventually snaps. It does not have a fuse. There is no clock ticking inside the neutron in the ordinary mechanical sense. A neutron that is 14 minutes old is not more likely to decay in the next second than a neutron that was born half a second ago. Each neutron, at every moment of its existence, has exactly the same tiny probability per unit time of undergoing this weak transformation. It is a purely probabilistic event, governed by quantum mechanics, and it has no memory. That is a big deal, and it is worth pausing on. If you had a jar of 10,000 free neutrons, and you waited 14.5 minutes, roughly half of them would have decayed. If you then took the surviving ones and put them in a fresh jar and waited another 14.5 minutes, half of those would have decayed. And so on, all the way down until the last one was gone. There is no cohort of neutrons that decay early because they were tired, and no cohort that decays late because they were fresh. Every one of them plays a private lottery. When the ticket comes up, it changes into a proton, an electron, and an antineutrino, and then it is done. The randomness is not a lack of knowledge on our part, it is built into the physics. This memoryless, probabilistic quality is why physicists talk about a half-life or a mean lifetime rather than a fixed expiration date. Half-life is just the point at which, statistically, half of a large group is expected to be gone. Mean lifetime is the average time a randomly chosen individual will live. For a free neutron, the mean lifetime is roughly 880 seconds, and the half-life is roughly 610 seconds. Those numbers say something about a huge population. They do not say anything you can rely on for a single neutron. A single free neutron might last 1 second. It might last 3 hours. On average, over enough of them, the numbers converge to those measured values. And now, having said all of that, we come to the pivot. We have described what the decay looks like, and we have described the force behind it, and we have described the fact that it is random and memoryless. But we have not yet answered the more basic question. Why does this happen at all? Why should a neutron ever change into a proton and an electron and an antineutrino, rather than just sitting there like the proton and the electron do? That is where the concept of energy comes in, and that is where the whole next stretch of the story is going to hinge. Because the reason the free neutron decays is not that the weak interaction reaches in and forcibly rewrites its identity. The weak interaction is capable of that, yes, but it is only allowed to actually complete the transformation if the arithmetic of energies on both sides works out. The neutron cannot become anything it wants. It can only become things whose combined mass and energy add up to less than what the neutron itself started with. Otherwise, the accountants of the universe simply refuse to sign off, and the decay does not happen. In the case of the free neutron, the arithmetic does work. Just barely, but it does. The mass of a free neutron, translated into energy by Einstein's famous equivalence, is slightly larger than the combined masses of a free proton, a free electron, and a free antineutrino. There is a small surplus. Not much. Less than 1 part in 1,000 of the neutron's total mass energy. But it is a real surplus. And it is that surplus that the electron and the antineutrino carry away as kinetic energy when they fly out of the decay. Without that surplus, the whole thing would be forbidden, and the free neutron would sit there quietly forever, just like the proton does. That single fact, that the free neutron is slightly heavier than its decay products, is what makes the free neutron unstable. And that same fact, viewed from a completely different angle inside a nucleus, is exactly what we are going to have to re-examine when we ask why a bound neutron can sit for billions of years, while its free cousin cannot last a quarter of an hour. The bound neutron is playing the same quantum lottery. The weak interaction is still there. The rules of the game have not changed. What has changed is the environment, and specifically, what has changed is the total energy ledger that any attempted decay would have to satisfy. So the free neutron dies. It dies because a very rare virtual event, a fleeting appearance of a heavy weak boson inside its interior, has enough room to complete itself, because the sum of the outgoing particles is slightly lighter than the incoming one, and because the arithmetic allows it. On average, that random event finally arrives after about 14.5 minutes. Before we can explain why bound neutrons in stable atoms do not die at all, we need to look much more carefully at that energy arithmetic. And that is exactly where we are going next. Energy conservation is not a suggestion that nature follows most of the time. It is one of the strictest rules there is, verified in every experiment ever performed to whatever precision was available, and no physicist has ever seen it broken in a way that survived scrutiny. Whatever comes out of a reaction has to add up, in the end, to exactly what went in. Not a little more, not a little less. Exactly the same once you have counted mass, kinetic energy, radiation, and every other form that energy is able to take. If the books do not balance, the reaction is not just unlikely, it is impossible. It simply will not happen. That is the invisible bouncer standing at the door of every possible decay in nature, and it is the bouncer we have to properly introduce now, because the entire fate of the free neutron is decided by whether it can find a doorway whose books balance in its favour. The place to start is a piece of physics almost everyone has heard of and almost nobody has really absorbed at the level we need. Mass is a form of energy, not a container that holds energy inside it, not something separate that can be traded for energy under special conditions. Mass simply is energy, expressed in a different accounting unit. Einstein's most famous equation, E equals mc squared, is not really a formula for converting one thing into another. It is a translation guide between two ways of measuring the same underlying quantity. The m on one side is measured in kilograms. The e on the other side is measured in joules. The c squared in between is a very large conversion factor, because the speed of light squared is an enormous number when you write it out in ordinary units. But the equation itself is saying that every gram of mass sitting quietly is already carrying an enormous amount of energy encoded inside itself. In particle physics, everyone eventually gets tired of translating back and forth between kilograms and joules for objects that are a trillion times lighter than a paperclip. So they use a unit called the electron volt. 1 electron volt is the energy an electron picks up when it falls through a potential difference of 1 volt. It is a very small unit, perfect for particles. Its cousins, the kilo electron volt, the mega electron volt, and the giga electron volt, cover the range of energies where nuclear and particle physics actually live. And because mass and energy are the same thing in different units, physicists just quote the mass of a particle in these energy units too. When they say the proton has a mass of about 938 mega electron volts, they mean the energy it would take to create one from scratch, or, equivalently, the energy you could get back if you could somehow annihilate one entirely. With that in hand, we can now write down the actual numbers that decide the neutron's fate. And these numbers are worth taking seriously, because everything hinges on their difference. The mass of a neutron, expressed as an energy, is about 939.5 mega electron volts. Precisely, it is closer to 939.565 mega electron volts, but for our purposes, think of it as sitting just below 940. The mass of a proton, in the same units, is about 938.27 mega electron volts. So the neutron is heavier than the proton, and the difference between them is about 1.293 mega electron volts. Not much next to the huge quantity on either side of the balance, barely more than 1 part in 1,000. But it is a real difference, and it is what everything else will hang on. Now bring in the other players. The electron that gets born during the decay has a mass, expressed as energy, of about 0.511 mega electron volts. That is about 511,000 electron volts, comfortably smaller than the difference we just calculated. And the electron antineutrino, the ghostly third particle, has a mass so small that even today no experiment has been able to pin it down exactly. All that has been established is that the antineutrino's mass, in energy units, is somewhere below about 1 electron volt, which is more than 500,000 times smaller than the electron's mass and completely negligible next to the numbers we are working with here. For the purposes of the energy balance, we can treat the antineutrino as if it were massless. It is not quite massless, but it is close enough that in this arithmetic the difference simply does not matter. Now do the sum. On one side of the balance sheet you have the neutron alone, weighing in at about 939.5 mega electron volts. On the other side of the balance sheet, you have 3 particles that could potentially replace it. A proton at 938.27, an electron at 0.511, and an antineutrino at essentially 0. Add the three together, and you get about 938.78. Compare that to the neutron. The neutron is about 0.78 mega-electron volts heavier than the sum of its potential decay products. That number, roughly 780,000 electron volts of surplus, is the entire reason the free neutron cannot stay. In the language of nuclear physics, it is called the Q value of the decay. Q values that are positive mean the reaction gives off energy. Q values that are negative mean the reaction would have to absorb energy from somewhere, which is generally not available in a quiet vacuum. The neutron's beta decay has a Q value of about 782,000 electron volts, and it is positive, and that positivity is exactly what makes the decay possible. Think about what this actually means physically. If you were somehow able to place a neutron on the world's most precise scale, and put on the other side of that scale a proton, an electron, and an antineutrino, all sitting perfectly still and doing nothing, the neutron side would tip down slightly. It would have more mass. And in a universe where mass is energy, that means the neutron, sitting quietly by itself, is carrying more total energy than it would if it were replaced by those three particles sitting quietly at the same location. It is uphill from where it could be. And in nature, anything that is uphill and is allowed to roll downhill will eventually, statistically, sooner or later, do so. The 782,000 electron volts of surplus have to go somewhere when the decay happens, because energy is not destroyed, only rearranged. It cannot just vanish. And the electron and the antineutrino, the two particles that are flying out and are not the proton, are exactly where it goes. That surplus becomes kinetic energy of the outgoing electron and antineutrino. They carry it away with them, whizzing off into whatever space is available, distributing that extra energy between their motion. This is where beta decay reveals something surprisingly subtle. Because there are two particles carrying away the leftover energy, and because they can share it in different proportions depending on how the decay happens to play out, the electron does not fly out with a fixed, predictable amount of energy. Sometimes almost all of the surplus goes to the electron, and almost none to the antineutrino. Sometimes it is the other way around. Most of the time it is somewhere in between. If you measured the energies of the electrons flying out of a large sample of decaying neutrons and made a graph, you would get a smooth, continuous curve, running from nearly zero energy up to nearly the full Q value at the top end. This continuous spectrum was actually one of the great puzzles of early 20th century physics. In the 1920s, when physicists first measured the energies of beta electrons coming out of nuclei, they were baffled. Every other kind of nuclear decay they had studied gave out particles with sharp, definite energies. Alpha particles, for instance, came out at very specific energies, characteristic of their parent nucleus. But beta electrons refused to cooperate. Their energies smeared out over an entire range. It looked like energy was not being conserved, and physicists as serious as Niels Bohr briefly wondered whether energy conservation might have to be abandoned for beta decay. The resolution came in 1930 from Wolfgang Pauli, who wrote a famous letter to a physics meeting he could not attend, apologizing that he was proposing a desperate remedy to save energy conservation. His remedy was the neutrino. He suggested that a third, invisible, extremely light and electrically neutral particle was being produced alongside the electron in every beta decay, silently carrying away whatever fraction of the energy the electron did not get. That would explain the continuous spectrum. The two particles would share the fixed total in whatever ratio they happened to share it, and the electron alone would look like it was violating the rules only because we were forgetting to look at its invisible companion. Pauli was correct. What we now call the electron antineutrino, and what he had originally proposed, do the job perfectly. Every measured beta electron energy from every measured neutron decay fits neatly under a curve that peaks somewhere in the middle and reaches a hard maximum at exactly the Q value we calculated. The end point of that spectrum the very highest possible electron energy that has ever been observed, matches the mass difference we would predict from the neutron mass, minus the proton mass, minus the electron mass, to the precision of the measurement. Energy conservation is not violated. It is honored to the letter. The books balance perfectly. It just took the discovery of an entirely new particle to prove it. Pauli himself worried, when he made his proposal, that he had done a terrible thing by inventing a particle that could never be detected. His reasoning was that any particle light enough and electrically neutral enough to have escaped everyone's notice would also, by the same tokens, interact so weakly with ordinary matter that it might never be caught. He thought he had proposed something unfalsifiable, and that troubled him deeply. It nagged at him for decades. He was wrong about the unfalsifiable part, but only barely, and only after 26 years of technological progress. It took until 1956 for Clyde Cowan and Frederick Rhines to finally catch an antineutrino in the act. They did it by parking a giant tank of water laced with cadmium chloride next to the Savannah River nuclear reactor in South Carolina. The reactor produced antineutrinos in enormous numbers because every fission event inside it eventually produced neutron-rich fragments that beta-decayed, sending antineutrinos out as a byproduct. The tank of water was there to catch the extraordinarily rare event in which one of those antineutrinos, on its way through the tank, happened to smack into a proton and convert it into a neutron and a positron. The signature was extremely specific. The positron would annihilate almost immediately with an electron, producing 2 gamma rays. The freshly born neutron would wander for a few microseconds and then be captured by a cadmium nucleus, which would release its own characteristic gamma ray in response. Cowan and Rhines built detectors capable of seeing all 3 gamma rays and confirming that they arrived in the exact temporal sequence that antineutrino capture demanded. When they finally saw the signal, they sent Pauli a telegram. He replied that he had waited 26 years for the news, and that everything comes to him who knows how to wait. The antineutrino was real. Energy conservation had been vindicated, and a particle that Pauli had privately worried might be philosophically illegal turned out to belong to one of the most abundant particle families in the universe, with something like 100 trillion neutrinos of all kinds streaming through every square meter of the Earth's surface every second, coming from the Sun and from every reactor and star. There is a small and useful lesson tucked inside this story that will matter enormously in a moment when we look at what actually determines how fast a neutron decay proceeds. The reason phase space matters so much, and specifically the maximum energy available to the outgoing particles, is that quantum mechanics counts the number of accessible final states, and that count grows explosively with available energy. Roughly speaking, doubling the energy budget for the outgoing electron and antineutrino gives them not just twice as many places to go, but many times more, because both particles can share the energy in a huge range of ways, and each way corresponds to a distinct final state. That explosive scaling is why the neutron decay rate is so sensitive to the Q value. A little more surplus energy, and the rate jumps dramatically. A little less, and the decay slows down out of all proportion. That fact is going to matter a great deal when we start looking at bound neutrons, whose Q values are set by the whole surrounding nuclear system, rather than by the neutron alone. So the free neutron has a way out. It is heavier than what it could become. The weak interaction offers a path down that slight energy hill. The electron and the antineutrino, born in the transformation, carry the leftover energy off as motion. Everything conserves. The arithmetic is legal. That is only the first half of the story, though, because being allowed to happen is not the same as being required to happen. Plenty of things in nature are allowed and simply take their sweet time about it. What we still need to explain is why this particular allowed transition takes about 14.5 minutes on average to occur, and what determines that number. Because if all that mattered were the energy balance, you might expect a neutron with such a nice positive Q value to just fall apart the moment it exists. It clearly does not. Something is holding it back, even though nothing is technically preventing it. The thing holding it back is the sheer improbability of the process at the quantum level. Remember, the transformation involves a heavy virtual W boson appearing inside the neutron for the briefest imaginable moment. Even though the neutron has enough total energy budget to eventually pay for the transition, arranging for that transition to actually happen requires a very specific and rare quantum event. The quark has to have just the right kind of interaction with the weak field at just the right moment. And the strength of the coupling between quarks and the weak field is very small compared to the strength of, say, the coupling between quarks and the strong field. That is what weak really means as a name for this force. It is not weak in the sense of being feeble at any energy. It is weak in the sense that it hardly ever fires. Physicists have a beautiful piece of quantum mechanics called Fermi's Golden Rule, which puts numbers on how often such rare processes occur. In plain language, the rule says that the rate of any quantum transition depends on two things. First, on how strongly the initial state and the final state are connected by whatever force is doing the mediating. Second, on how much room there is in the final state for the products to land in. That second factor is called the phase space, and it is largely determined by how much surplus energy is available for the outgoing particles to share. For the free neutron, the coupling piece of the answer is small, because the weak interaction is small. That is what makes the free neutron survive minutes rather than nanoseconds. And the phase space piece is also modest, because the surplus energy is only 782,000 electron volts, which is small on the scale of particle physics. Together, those two factors give a very slow decay rate. Slow enough that the average neutron waits about 14.5 minutes before its number comes up. But it will come up. That is the key. Because the process is allowed, and because it does have a non-zero rate, the probability of decay per unit time is not exactly zero. And any non-zero probability, extended over enough time, adds up to a certainty. If you sit and watch one free neutron for long enough, you will eventually see it decay. If you watch 1,000,000 of them, half of them will be gone within about 10 minutes. That is what a positive Q value guarantees. The weak interaction is not going to skip its turn forever. Eventually, on whatever timescale it likes, the transition happens. This is worth dwelling on because it points at something that is going to matter enormously in a moment. A free neutron does not fall apart because of anything mechanical. There is no wear. There is no internal fatigue. There is nothing inside it counting down. Every instant of its life is exactly like every other instant from the neutron's own point of view. What makes it unstable is entirely external to it in a certain sense. It is the fact that the universe offers a lower energy configuration of the same conserved quantities, and offers a mechanism, the weak interaction, that can eventually get the neutron into that configuration. The neutron is not unhappy where it is. It is not straining to escape. It is just sitting there. But there is a doorway to somewhere lower, and quantum mechanics guarantees that any door that is even slightly open will eventually be walked through. Here is a way of picturing it that might help. Imagine a ball resting on a small ledge on the side of a cliff. The ball is perfectly still. Nothing is pushing it. But it is sitting on a ledge, and the ledge is above a lower ledge, and to get to the lower ledge, the ball has to somehow tumble off. If the transition is fast and easy, the ball tumbles almost immediately. If the transition is difficult, requires a very specific push, or requires quantum tunneling through a barrier, the ball may sit on the higher ledge for a very long time before, Finally, unpredictably, it makes the trip. The free neutron is a ball on a slightly higher ledge. The lower ledge is a state consisting of a proton, an electron, and an antineutrino, with about 782,000 electron volts of kinetic energy shared between the electron and the antineutrino. The transition is difficult because the weak interaction is a very reluctant mediator. So the neutron sits on its ledge, on average, for about 14.5 minutes. Then it makes the trip. Once it has made the trip, it is not coming back, because the reverse process, in which a proton and an electron and an antineutrino spontaneously combine to reform a neutron, would require them to add energy from somewhere to climb back uphill, and in the quiet vacuum where the free neutron was decaying, that energy is not just lying around waiting to be picked up. This picture of stability being about whether there is a lower ledge to fall to is the picture that generalizes. And it is the picture we now have to carry with us as we start thinking about what happens to a neutron that is not free. Because the entire question of whether a bound neutron is stable is going to come down to exactly the same principle. Is there a lower ledge available? If yes, then given enough time, and assuming the weak interaction can bridge the gap, the neutron will eventually take the trip. If no, then no. That is it. There is no other consideration. The trick, and it is a very deep trick, is that a neutron inside a nucleus is no longer facing the same ledge it was facing when it was alone. The lower ledge that a free neutron was going to fall onto, a proton plus an electron plus an antineutrino, does not exist as an isolated menu option for a bound neutron. Because you cannot just remove one neutron from a nucleus, turn it into a proton, and leave everything else the same. A nucleus is not a bag of independent particles. It is one connected quantum object. If the neutron changes identity, the entire nucleus changes identity along with it. And the total energy of the new nucleus, the daughter nucleus, is a completely different quantity from the total energy of the original. That is the subtle point that flips the whole picture. And that is why we cannot answer the question of neutron stability by looking at the neutron alone. We have to look at everything the neutron is bound to and ask what the entire assembly would look like on the other side of the transition. Sometimes the assembly on the other side sits at a lower total energy than the assembly on this side, and the decay happens. Sometimes it sits at a higher total energy, and the whole event is forbidden by the same energy conservation rule that made the free neutron decay possible in the first place. Same rule, different arithmetic, different result. Before we go there though, hold on to the free neutron picture one more time, cleanly, because it is going to be our baseline for the rest of the story. A free neutron alone in empty space carries slightly more mass energy than a free proton, a free electron, and a free antineutrino sitting quietly at rest. That surplus, small as it is what makes decay energetically legal. The weak interaction is what actually carries out the transition, slowly, unwillingly, on average once every 14.5 minutes. There is no clock, there is no wear. There is only a fixed probability per unit time, drawn from the strength of the weak coupling and the available phase space, playing out through the memoryless mathematics of quantum decay until, at some unpredictable instant, one particular neutron happens to succeed at the transition and disappears. That is the whole story of the free neutron's fate, told in the language of energy. Take a neutron. Ask whether it has anywhere lower to go, given the conservation laws and the forces available. If yes, and if any force can mediate the trip, wait long enough and it will go. If not, it will sit there forever, exactly like the proton does, exactly like the electron does. Free neutrons happen to fall on the yes side of this test, and by a very small margin. Everything else follows from that margin. The question we are about to open is what happens to that margin when the neutron is no longer alone. Because as it turns out, walking into a nucleus can change the arithmetic completely. Sometimes it can widen the margin, and the neutron becomes even more unstable than before. Sometimes it can shrink the margin, And sometimes, remarkably, it can flip the sign of the margin altogether, so that the neutron is no longer sitting on a higher ledge with somewhere to fall, but on the lowest ledge available, with nowhere further down to go. When that happens, the neutron simply stays put. Not for minutes, not for hours, forever, or as close to forever as any experiment has ever been able to measure. The weak interaction is still there. The neutron is still made of the same quarks. Nothing about the particle itself has changed. What has changed is the shape of the energy landscape around it, and that turns out to be everything. To understand what happens to a neutron once it steps into a nucleus, we have to abandon a picture that almost everyone carries around without realizing it. The picture is this. An atomic nucleus is a little cluster of protons and neutrons stuck together, like a bag of marbles. Each marble is a self-contained particle, sitting next to the others, occasionally jostling them but otherwise minding its own business. If you asked about the mass of the nucleus, you would add up the masses of all the marbles in the bag, and that would be your answer. That picture is wrong in an important way, and the way in which it is wrong is the entire reason the story we are telling exists. When you actually go and measure the mass of an atomic nucleus carefully and precisely, and then compare it to the sum of the masses of the protons and neutrons that supposedly make it up, you find that the nucleus is always lighter than the sum of its parts. Not by a huge amount, usually less than 1%, but by an amount that is far too large to be a measurement error, and one that shows up cleanly in every nucleus that has ever been examined. A helium nucleus made of 2 protons and 2 neutrons weighs less than 2 protons plus 2 neutrons on their own. A carbon nucleus made of 6 protons and 6 neutrons weighs less than 6 protons plus 6 neutrons standing separately. An iron nucleus, deep in the periodic table, is even more strikingly lighter than the sum of its individual pieces would suggest. It is as if putting the pieces together caused mass to quietly disappear. Mass does not actually disappear. What disappears is a very specific kind of energy, and it is the same idea we have been chasing this whole time. When you bring protons and neutrons together to form a nucleus, the strong nuclear force pulls them into a deep energy well. Getting into that well releases a large amount of energy, which the pieces radiate away as they settle. Once they are in the well, they are more tightly bound than they were as separate particles, which is another way of saying they sit at a lower total energy. And because mass is energy, the assembled nucleus, sitting at a lower total energy than its scattered pieces, actually weighs less than those pieces. The amount of energy that had to be released to assemble the nucleus is called the nuclear binding energy. It is the invisible price the pieces paid to become part of a whole, and it shows up as missing mass whenever you weigh the finished nucleus. If you wanted to pull the nucleus apart again and separate the individual protons and neutrons, you would have to put back exactly that much energy. The binding energy is not stored somewhere inside the nucleus like a battery. It is the energy that is already gone. It is a debt the universe collected when the nucleus was made, and the nucleus cannot be taken apart without paying that debt back. Every stable nucleus in nature has a positive binding energy, which is another way of saying that every stable nucleus is more strongly held together than the sum of its individual pieces would be if they were on their own. That is the entire reason nuclei exist as stable objects. If putting protons and neutrons together did not release energy, there would be nothing keeping them together against the electric repulsion of the protons, and there would be no atoms and no chemistry and no anything. The binding energy is what makes matter matter. Now here is the important part, and this is where the story we are telling starts to open up. The binding energy per nucleon, meaning the average amount of energy given up by each proton or neutron when it joins a particular nucleus, is different for different nuclei. It is not a universal constant. Some nuclei are more tightly bound than others. Iron and nickel in the middle of the periodic table are the champions. Each proton and neutron in an iron nucleus has surrendered roughly 8.5 million electron volts of energy to join the assembly. That is enormous compared to the 782,000 electron volts we were talking about in the free neutron's decay. It is a much steeper energy well. Very light nuclei, like the deuteron, which is one proton and one neutron stuck together, are less strongly bound. Each of their nucleons has given up only about 1 million electron volts to join. Very heavy nuclei, like uranium, are also less strongly bound per nucleon than iron. Somewhere in the middle, iron sits at the bottom of the deepest well nature offers. That variation, that difference in binding energy per nucleon from one nucleus to the next, is what powers the Sun. Nuclear fusion works by pushing lighter nuclei together into heavier ones that are more tightly bound, releasing the difference as energy. Nuclear fission works by splitting very heavy nuclei into medium ones that are more tightly bound, releasing the difference as energy. And beta decay, our subject, is going to work by taking one nucleus and converting it into a neighboring nucleus that is, if the conditions are right, more tightly bound than the original. Nature is constantly trying to sink into the deepest available well. Every stable nucleus is one that has already found the deepest well available to it, given the number of protons and neutrons it has to work with. But it is not enough to know that a nucleus has a certain binding energy. To understand what happens to a bound neutron, we have to look more carefully at what it actually means to be bound. Inside a nucleus, protons and neutrons are packed together into a volume so small that if you scaled the nucleus up to the size of a marble, the atom around it would be roughly the size of a football stadium. They are pressed together so tightly by the strong nuclear force that they are essentially touching. And they are not sitting still. They are moving, colliding, exchanging identities in certain quantum senses, occupying discrete energy levels that are set by the geometry of the well they are in and the rules of quantum mechanics. That last point is the one to hold on to. The protons and neutrons inside a nucleus do not have arbitrary energies. They occupy quantum states in exactly the same way that electrons around an atom occupy quantum states with specific energies. There are ground states, which are the lowest energy configurations available. There are excited states, which are configurations of higher energy. And there is a rule called the Pauli exclusion principle, which says that no two identical particles of a certain type can occupy the same quantum state simultaneously. Protons obey this rule with respect to other protons. Neutrons obey this rule with respect to other neutrons. But protons and neutrons are different species of particle, so a proton does not block a neutron from a state, and vice versa. What this means, in practice, is that inside any nucleus, the protons fill up their available quantum states, starting from the lowest energy one and working upward, and the neutrons fill up their available quantum states, starting from the lowest energy one and working upward. And these are two separate stacks, two separate ladders. Each ladder is being filled from the bottom. Picture two side-by-side ladders inside the nucleus, one for protons and one for neutrons. The rungs represent quantum energy levels. Each rung can hold at most a small number of particles, usually two of each type, because of some additional subtlety about spin. You start filling the ladders from the bottom rung and work up. If you have 6 protons and 6 neutrons, you fill the bottom few rungs of each ladder. If you have 26 protons and 30 neutrons, like an iron nucleus, you fill quite a lot of rungs. The last occupied rung on each ladder sets what physicists call the Fermi level for that species. Everything below the Fermi level is packed with particles. Everything above it is empty. This ladder picture is a simplification, but it captures the essential feature we need. Neutrons in a nucleus are stacked into occupied quantum states up to a certain neutron Fermi level. Protons in the same nucleus are stacked into their own set of occupied quantum states up to a certain proton Fermi level. The two Fermi levels do not have to be at the same energy, and in fact, they often are not. Which one is higher depends on the specific nucleus. Now imagine what would have to happen for a bound neutron inside this nucleus to decay the way a free neutron does. In free space, one of the down quarks inside the neutron flips into an up quark. The neutron becomes a proton, and outfly an electron and an antineutrino. Fine. Try to run the same story inside the nucleus. One of the down quarks inside one particular bound neutron flips into an up quark. That specific bound neutron becomes a bound proton. But now you have a problem. The nucleus you started with had, let us say, 26 protons and 30 neutrons. After the transition, it has 27 protons and 29 neutrons. It is now a different element, a different nucleus, with a completely different arrangement of quantum states and a completely different total binding energy. That is the pivot. In free space, when a neutron decays, the products are three isolated particles that carry off the surplus energy and go their separate ways. In a nucleus, when a neutron tries to decay, the products are not three isolated particles at all. They are an electron flying away, an antineutrino flying away, and, crucially, an entirely different daughter nucleus left behind. The daughter nucleus has one more proton and one less neutron than the parent. Its shape, its binding energy, its filled quantum states are not the same as the parent's. It is a different chemical element, a different isotope, a different quantum object. That means when you ask whether the decay is energetically allowed inside a nucleus, you cannot just compare a neutron's mass to a proton plus an electron plus an antineutrino. You have to compare the total mass of the parent nucleus to the total mass of the daughter nucleus plus the electron plus the antineutrino. And because binding energies are much larger than the free neutron's 782,000 electron volts of surplus, the difference between the parent nucleus's mass and the daughter nucleus's mass has essentially nothing to do with the mass difference between a neutron and a proton in isolation. It has almost everything to do with the difference in binding energy between the parent and the daughter. To make this concrete, consider what happens numerically. Take carbon-12. It has 6 protons and 6 neutrons. Its binding energy is about 92 million electron volts. Now imagine one of its neutrons trying to beta decay. The daughter nucleus, if that were to happen, would be nitrogen-12, 7 protons and 5 neutrons. The binding energy of nitrogen-12 is about 74 million electron volts, so the parent, carbon-12, is bound by about 92 million electron volts, and the potential daughter, nitrogen-12, is bound by only about 74 million electron volts. That is an enormous difference, roughly 18 million electron volts less binding in the daughter than in the parent. What does that mean for the energy balance? Remember, being more tightly bound means sitting at a lower total energy. Carbon-12 sits 18 million electron volts lower than nitrogen-12 would when you account for their binding differences. So converting a neutron in carbon-12 into a proton, if that were possible, would take you from a lower energy state to a much higher energy state. You would have to supply energy from somewhere just to make the transition happen. But the surplus you have available from converting a neutron to a proton in isolation is only about 782,000 electron volts. That is nowhere near enough to climb the 18 million electron volt hill created by the loss of binding energy. The books do not balance, not even close. The transition would require, on net, about 17.2 million electron volts to come from nowhere. No source of energy is available. The vacuum around the nucleus is not going to spontaneously donate 17 million electron volts. Cosmic rays occasionally do, but that is not spontaneous decay. In quiet, ordinary conditions, the transition is simply forbidden by energy conservation. The neutron in carbon-12 sits there. It does not decay. It cannot decay because there is nowhere to go that has lower total energy than where it already is. And this is the point where the story becomes shocking once you see it clearly. The neutron inside a carbon-12 nucleus is still, in every intrinsic sense, the same particle it would be in isolation. It is still made of two down quarks and an up quark. It is still slightly heavier than a proton on its own. The weak interaction is still available. Nothing about the neutron itself has stopped being what it was. And yet it will not decay, because the daughter nucleus it would have to leave behind is at a higher total energy, and no matter how badly the individual neutron might in principle want to become a proton, the accountants of the universe will not sign off on a transaction that would require energy to appear from nowhere. So the neutron stays. Not by force, not because it is being blocked, because there is simply no legal transition it can make. That, in essence, is the mechanism. The nucleus rearranges the energy landscape around the neutron. It changes what the neutron would have to become, and it changes how much energy that becoming would cost or release. In some nuclei, the rearrangement makes the transition impossible. In other nuclei, we will see, the rearrangement leaves the transition still possible, but slower, or makes it just as favorable as before, or, in a few remarkable cases, makes it easier than it would have been for a free neutron. But in the case of carbon-12 and oxygen-16 and every other stable nucleus, the rearrangement is fatal to the possibility of decay. The bound neutron sits at the bottom of a well that has no lower level to fall into. It rests. There are two other pieces to the story that are worth pulling into the picture at this point, because they help explain why nuclei happen to sit in stable configurations rather than lopsided ones. The first has to do with the Pauli exclusion principle, and the second has to do with a peculiar electromagnetic penalty that comes with adding protons. Take the Pauli exclusion story first. Remember the two side-by-side ladders. Neutrons stacked in one, protons in the other, each filled up from the bottom. If the neutron ladder has extra rungs occupied above where the proton ladder ends, then the highest neutron sits at higher energy than the highest proton. In that case, converting a top neutron into a proton means moving from a high rung on the neutron ladder to a lower rung on the proton ladder. That is going downhill in a certain quantum sense, and it means the transition might be energetically favorable. Nature, if it can, will try to equalize the ladders. Now flip it. Suppose the two ladders are already balanced, with neutrons and protons filling roughly the same number of rungs at roughly the same energies. Turn one top neutron into a proton, and you would be trying to put a proton onto a rung of the proton ladder that is already occupied. That is not allowed. So the newborn proton has to go into a higher, unoccupied proton rung. But the top of the neutron ladder was at a certain energy, and the next available proton rung is at a higher energy. So converting the neutron would mean going uphill. That costs energy. That closes the door. This is why, when you look at stable light nuclei, the number of neutrons is very close to the number of protons. 6 protons and 6 neutrons for carbon-12, 8 and 8 for oxygen-16, 20 and 20 for calcium-40. In each case, the two ladders are approximately balanced, and there is no easy way to convert one species into the other without going uphill somewhere. That equality of neutron and proton counts, driven by the exclusion principle, is one of the reasons stable nuclei favor certain proton-to-neutron ratios and not others. But that is not the only pressure. There is a second one, and it points in the opposite direction. Protons repel each other electrically. Two protons sitting side by side in a nucleus feel a strong Coulomb repulsion trying to push them apart. Neutrons do not feel this repulsion because they carry no net electric charge. So, having lots of protons is expensive. Every proton you add to a nucleus makes it more difficult to hold the whole thing together, because every proton adds to the total repulsive push acting on every other proton. This penalty grows quickly as the nucleus gets bigger, because there are more and more pairs of protons all pushing against each other simultaneously. To fight this proton repulsion, heavier nuclei tend to add extra neutrons. Neutrons contribute to the strong force binding, which is attractive, but they do not contribute to the electrical repulsion. So they are, in a sense, cheap glue. They help hold the nucleus together without adding to the pressure that is trying to blow it apart. That is why, as you go to heavier and heavier elements, the ratio of neutrons to protons in the stable isotopes steadily rises. Iron, at 26 protons, is stable with 30 neutrons. Lead, at 82 protons, is stable at around 126 neutrons in its most common isotope. That imbalance, favoring more neutrons than protons, is what heavy nuclei need to survive the electromagnetic pressure of packing all those protons together. Notice what these two pressures are doing at the same time. The exclusion principle wants roughly equal numbers of protons and neutrons, because that keeps the two ladders balanced and avoids wasting energy on high, empty rungs. The electromagnetic repulsion wants more neutrons than protons, because more neutrons help dilute the repulsive push. Any given nucleus is a compromise between these two competing pressures. The exact place where the compromise sits, for a given total number of nucleons, determines which combination of protons and neutrons is the most tightly bound. And that most tightly bound combination is the one that sits at the very bottom of the energy well. A neutron inside that most tightly bound combination has nowhere to go. Any transition would move the nucleus off the bottom of the well, uphill, in violation of energy conservation. So the neutron waits, permanently, doing nothing. That is what makes it stable, and this is worth stating cleanly because it is easy to misread. The stability of that neutron is not a property of the neutron. It is a property of the entire nucleus around it. The same particle, extracted and placed in empty space, would begin its 14-minute countdown immediately. Nothing about the particle would have changed. What would have changed is the environment. In empty space, there is a lower energy configuration available, and the weak interaction can eventually get the neutron there. Inside a well-chosen nucleus, no lower energy configuration is available. The path is not just slow, it is not just improbable, it is not there at all. There is a common misconception worth killing at this point, because it comes up all the time and it makes the whole subject harder to think about. The misconception is that the strong force somehow reaches into the neutron and holds it together against decay, like a cage around the marble, keeping it from breaking. This is not what is happening. The strong force is what binds nucleons to each other. It creates the energy well. It does not reach in and clamp down on the internal quark structure of the neutron and prevent the weak interaction from doing its thing. The weak interaction inside a bound neutron is still perfectly capable of trying to fire. What stops it is not a competing force. What stops it is arithmetic. The final state after firing would have higher total energy than the state before firing, and energy conservation is not something you can argue with by turning up any dial. The transition just does not happen because the numbers do not add up. Equally, it would be wrong to say that the nucleus is a hard cage that physically traps the neutron and prevents it from leaving. The neutron is not trying to leave. Decay is not a form of escape. Decay is an internal transformation, one quark flipping species. The nucleus does not need to physically restrain the neutron. It only needs to be arranged so that if the neutron did transform, the resulting daughter nucleus plus outgoing particles would sit higher on the energy ladder than the current configuration. When that is the case, the transformation simply is not an option. The neutron is not caged. The neutron is at the bottom of the well. We are now in a position to see the whole story from a new angle. When we asked why a free neutron dies, the answer had to do with a positive Q value, a small mass surplus, a slow but non-zero weak interaction rate, and enough patience to wait through 14 minutes on average. When we ask why a bound neutron in a stable nucleus lives, the answer has to do with the fact that the same Q value calculation, done for the full nuclear system rather than the isolated neutron, comes out negative. There is nowhere lower for the whole system to go. The 782,000 electron volts of surplus that the isolated neutron could offer is dwarfed by the binding energy shifts that would accompany turning it into a proton. The extra binding of the parent nucleus, or equivalently, the reduced binding of the daughter nucleus, is what closes the door. And notice something remarkable. Notice how completely different environments produce completely different fates for what is physically the same little bag of quarks. A neutron floating alone in a beamline at a research reactor lives roughly 14.5 minutes on average. That same neutron, if it could somehow instead find itself embedded inside a carbon-12 nucleus, would sit there for as long as the carbon-12 nucleus itself lasts, which, as far as anyone can measure, is forever. The particle did nothing to earn either fate. It did not become more stable by being clever, and it did not become more unstable by being lonely. The environment changed, the energy landscape changed, and with it, the possibility of decay flipped from allowed to forbidden. That is the mechanism in its cleanest form. That is the trick nuclei play with the neutrons they contain. Nuclear binding does not turn off the weak interaction. It does not add a competing force that cancels it out. It changes the arithmetic of what would happen if the weak interaction did fire. And in most stable nuclei, it changes it in a way that makes the firing pointless. Not blocked, not opposed, just not allowed by conservation of energy. The story is not quite over, because not every bound neutron sits at the bottom of the well. Some sit on ledges that are still above lower ledges, just as free neutrons do. In those nuclei, the door has not been closed, it has only been reshaped. And when the door is still open, even inside a nucleus, the neutron will still, eventually, take the trip. That is the last piece of the picture we need to assemble. Not every neutron inside a nucleus is sitting at the bottom of the well. That is the crucial next fact, and it is the fact that keeps the story from collapsing into a false symmetry. If we said only that bound neutrons are stable and free neutrons decay, we would be leaving out at least half of what actually happens in nature. Because for every stable isotope in the periodic table, there are many unstable ones. And in those unstable ones, bound neutrons very much do decay, on schedules that range from a fraction of a second to millions of years. The weak interaction is not asleep in those nuclei. It is working exactly as it always does. The difference is that in those nuclei, the energy landscape still slopes downward from where the neutron is, and so the door is still open. To see how this works, we have to think a little more carefully about what makes a nucleus stable in the first place, and what happens when you try to build a nucleus that is not stable. Every element in the periodic table is defined by its number of protons. 6 protons makes carbon, 7 makes nitrogen, 8 makes oxygen. But for any given number of protons, nature usually allows more than one possible number of neutrons. Different neutron counts with the same proton count are called different isotopes of the same element. Carbon can exist with 6 neutrons, giving carbon-12, or with 7 neutrons, giving carbon-13, or with 8 neutrons, giving carbon-14. All 3 are carbon, chemically identical, because chemistry only cares about electrons, which only care about protons. but they are physically different nuclei with different binding energies and different fates. Carbon-12 and carbon-13 are both stable. Their neutrons are locked at the bottom of the well we described. But carbon-14 is not stable. It has 2 more neutrons than carbon-12, and that extra pair of neutrons pushes the neutron ladder just a little higher than it needs to be, given the proton ladder underneath. There is a lower energy configuration available. Specifically, nitrogen-14, which has 7 protons and 7 neutrons, sits at a lower total energy than carbon-14 sits at. The 2 nuclei have the same total number of nucleons, 14 of them, but they distribute those 14 nucleons differently between the proton and neutron ladders. And nitrogen-14 happens to be the more tightly bound arrangement. That means the door is open. A neutron inside carbon-14 can, in principle, convert into a proton, turning the whole nucleus from carbon-14 into nitrogen-14, emitting an electron and an antineutrino along the way, and coming to rest in a lower energy configuration. The Q value for that decay is positive, not by much, about 156,000 electron volts of surplus, which is quite a bit smaller than the 782,000 electron volts a free neutron has to work with. But it is positive, and positive is what matters. The weak interaction, given enough time, will eventually make the transition happen. How long is enough time? For carbon-14, on average, about 5,700 years. That is the famous half-life that underlies radiocarbon dating, the technique archaeologists use to date old organic material. Every living thing on Earth is constantly incorporating carbon-14 from the atmosphere, where it is produced by cosmic rays hitting nitrogen. When the organism dies, it stops taking in new carbon-14, and the carbon-14 already inside it begins to decay away at that steady, memoryless rate. Measure how much is left, and you can work backward to figure out roughly when the organism died. The whole technique is possible because carbon-14 sits on a very shallow slope. The energy well of nitrogen-14 is only slightly deeper than the energy well of carbon-14. Not enough to make the decay fast, but enough to make it eventually inevitable. Notice what is different between carbon-14 and carbon-12. Both are made of protons and neutrons packed into a small volume. Both have neutrons that would, in isolation, decay in 14 minutes. The neutrons themselves are not special. What is special is the shape of the energy landscape around them. In carbon-12, that landscape has no lower point available. In carbon-14, it does. Same particle, same weak interaction, different environment, different fate. Notice also how big the range of decay times can be. A free neutron lives on average about 880 seconds, roughly 14.5 minutes. A neutron inside carbon-14 has an effective decay time on the order of thousands of years. The difference between those numbers is enormous, more than a factor of 100 million, and yet both are governed by the same weak interaction, with essentially the same intrinsic strength. What sets the difference is almost entirely the Q value. The free neutron has about 782,000 electron volts of surplus to play with. The bound neutron in carbon-14 has only about 156,000 electron volts. Fermi's golden rule tells us the decay rate depends strongly on the Q value, because the amount of phase space available for the outgoing electron and antineutrino grows rapidly as their maximum possible energy grows. A smaller Q value means much less phase space, means a much slower decay. That is why carbon-14 takes thousands of years rather than minutes. Take a different unstable nucleus and you get a different half-life. Tritium, which is hydrogen with 2 extra neutrons, decays into helium-3 with a half-life of about 12 years. Its Q value is even smaller than carbon-14's, only about 18,600 electron volts. Iodine-131, used in medical imaging, has a half-life of 8 days. Its Q value is much bigger, close to 1,000,000 electron volts. In each case, the decay is the same fundamental process. A bound neutron converts to a bound proton, producing an electron and an antineutrino. The energy balance is set by the difference in binding energy between the parent and the daughter, plus the mass difference between a neutron and a proton. If that combined Q value is positive, the decay is allowed, and the size of the Q value largely determines how fast the decay proceeds. You can look at this from a broader angle. Plot every known nucleus on a graph, with the number of protons along one axis and the number of neutrons along the other. Color in the stable ones. What you get is a band of stability running from the bottom left of the graph at very light nuclei up to the upper middle at nuclei with about 80 protons and 120 or so neutrons. That band is not perfectly straight. For the lightest nuclei, it hugs the line where the number of neutrons equals the number of protons. For heavier nuclei, it bends toward more neutrons than protons because of the electromagnetic repulsion story we told earlier. The band is thin, only a couple of isotopes wide at most, and it traces out what physicists call the valley of stability. Every stable isotope in nature sits in that valley. Anything outside the valley is unstable, and how it decays depends on which side of the valley it sits on. Nuclei above the valley have too many neutrons compared to protons. They have somewhere lower to go, and they get there by having one of their extra neutrons convert into a proton through beta decay. The neutron becomes a proton. The nucleus edges one step closer to the valley, an electron and an antineutrino fly out, and the total energy of the system drops. That is beta minus decay, exactly the same process we have been describing all along, and it is the story of neutron-rich nuclei climbing back down into stability. Nuclei below the valley have too many protons compared to neutrons. They have somewhere lower to go too, but in the opposite direction. Their protons want to become neutrons. There is a symmetric process called beta plus decay, in which a proton converts into a neutron, emitting a positron and a neutrino, instead of an electron and an antineutrino, and the nucleus edges one step closer to the valley from the other side. That process is not part of our story tonight, but it exists, and it obeys the exact same energy accounting. The direction of decay depends entirely on which side of the valley you started on. And at the bottom of the valley itself, the nuclei just rest. They have found the deepest well available to their particular combination of nucleons, and no beta decay in any direction is going to help them, because both directions lead uphill. Their neutrons stay neutrons, their protons stay protons. Nothing changes forever, or as close to forever as anyone can measure. There is a beautiful way to see this that connects back to the individual neutron. Take a free neutron. Its problem is that a free proton, a free electron, and a free antineutrino together weigh a tiny bit less than the free neutron does. So the free neutron has downhill available. Now take a neutron inside a nucleus at the bottom of the valley of stability. Its potential daughter nucleus, the one that would result if it converted to a proton, is at a higher binding energy deficit than the parent, meaning it is less tightly bound, meaning the total energy of the daughter, plus the emitted electron and antineutrino, is higher than the total energy of the parent. Uphill, forbidden. so the neutron does not go. But now, take a neutron inside a nucleus that is above the valley of stability. Its potential daughter nucleus is more tightly bound than the parent. The total energy of the daughter, plus the emitted electron and antineutrino, is lower than the total energy of the parent. Downhill, allowed. So the neutron eventually goes. The individual neutron in each of these three cases is the same. The forces are the same. What differs is the total energetic geography of the system it belongs to. That geography is what quantum mechanics computes when it decides whether a decay can happen. And that geography is what nuclear binding energy is really telling us about. There are some remarkable corner cases that make the point even more vividly. Consider a nucleus like potassium-40. It has 19 protons and 21 neutrons. It sits close to, but not exactly on, the valley of stability. It has two possible ways to decay. It can beta-minus decay, turning one of its neutrons into a proton and becoming calcium-40. Or it can beta-plus decay in the opposite direction, turning one of its protons into a neutron and becoming argon-40. Both are energetically allowed, because both calcium-40 and argon-40 are more tightly bound than potassium-40. Potassium-40 sits on a small hill, with lower ground on either side, and accordingly it decays both ways, with a strong preference for beta- over beta+, and a half-life of about 1.25 billion years. Some of its neutrons decay, some of its protons decay. The rest sit and wait. That two-directional decay is a wonderful confirmation of the whole picture we have been building. The neutron in potassium-40 is not intrinsically less stable than the neutron in calcium-40. What determines its fate is entirely whether the surrounding nuclear structure offers a lower energy destination. In calcium-40, no such destination exists, and the neutron sits forever. In potassium-40, a destination does exist, and eventually, over the course of 1 billion years or so, some of the neutrons take the trip. Consider now what happens at the extreme far end of the valley, where nuclei have piled up so many extra neutrons that they can barely hold together. Somewhere out there, beyond the last isotope that is stable in each element, is what is called the neutron drip line. That is the point at which adding one more neutron to a nucleus provides no binding at all. The next neutron would just fall out. Approaching that line, you find nuclei with dozens of unstable isotopes, each with a very large Q value for beta- decay, each with a very short half-life, some measured in fractions of a second. In these extreme neutron-rich isotopes, the neutrons are effectively as unstable as free neutrons, or even more so, because their Q values can be much larger than the free neutrons. The environment, which in the valley of stability protects the neutrons from decay, at the drip line does the opposite. It makes the decay urgent. That neutron-rich extreme is not just a laboratory curiosity. It is a large part of the story of how the universe made most of its heavy elements. When a massive star runs out of fuel and collapses into a neutron star, or when two neutron stars collide, enormous fluxes of free neutrons are produced. Those neutrons crash into existing nuclei, get absorbed rapidly, and push those nuclei far out beyond the valley of stability into extremely neutron-rich territory. Then, those neutron-rich nuclei beta-decay their way back toward the valley, one neutron at a time, over seconds or minutes or hours, converting themselves step by step into the heavier, stable elements we find today. Gold, platinum, uranium, thorium. All of them were built by a cycle of neutron capture followed by beta decay. Every time one of those bound neutrons converted into a proton, it was because the energy landscape of the daughter nucleus offered a lower well than the parents. Same weak interaction, same accounting. On a cosmic scale, that accounting built the heavy periodic table. That process is called the R process, where the R stands for rapid, because the neutron capture happens so quickly that a nucleus can absorb dozens of neutrons in a fraction of a second before beta decay has time to catch up. The result is a nucleus so far into neutron-rich territory that in a laboratory it would fall apart almost immediately. In the aftermath of a neutron-star collision, huge numbers of these overloaded nuclei form in an instant. Then, as the neutron bath dissipates, they have no more free neutrons to absorb, and they begin the long walk back toward the valley of stability. Each of them beta decays, then beta decays again, then again, converting one neutron at a time into a proton, marching sideways across the chart of nuclei until finally it lands on a stable isotope and stops. When astronomers detected gravitational waves from a neutron-star merger in 2017 and then saw the optical afterglow that followed, they were watching this process happen in real time. The characteristic glow of that afterglow, spectroscopically, showed evidence of freshly synthesized heavy elements. Gold and platinum and rare earth metals were being made in that collision, forged out of the beta decay of neutron-rich nuclei falling back into the valley of stability. The gold in a wedding ring, in the strict physical sense, was manufactured by exactly this arithmetic, playing out somewhere in the sky billions of years ago. Same particle, same weak interaction, same energy accounting we have been walking through the whole time. Coming back to Earth and back to ordinary matter, the picture we have arrived at is now complete. In every stable nucleus around us, in the iron in your blood, the calcium in your bones, the carbon in your muscles, the neutrons are locked in place, not by force, but by arithmetic. They are at the bottom of the local well. No transition to a lower energy state is available, so they simply do not transition. Their internal quark structure is exactly what it would be if you extracted them and put them alone in empty space. The weak interaction is exactly as active inside them as it would be in a free neutron. What is different is only the total energetic geography of the system they inhabit. And that geography, in stable nuclei, closes the door completely. In unstable nuclei, the door is not closed, but only narrowed to a smaller opening. The Q value is positive but small. Beta- decay is allowed but slow. So the bound neutron does decay, on a timescale that could be years or centuries or thousands of years, depending on exactly how narrow the opening is. And when it does, the nucleus rearranges, becomes something new, and the whole quantum landscape shifts around what used to be a neutron and is now a proton. There is one more principle worth stating cleanly, because it is going to determine how we finish the picture. The stability of a nucleus is not a property of the individual nucleons inside it. It is a property of the whole assembly. When we say a certain isotope is stable, what we really mean is that the total energy of that particular arrangement of protons and neutrons is lower than the total energy of any other arrangement of the same number of protons and neutrons that could be reached by any allowed transition. The nucleus is stable because it has already found the bottom. And each nucleon inside a stable nucleus is stable not because it has changed its own nature, but because the whole is stuck at the bottom and cannot climb any hill to somewhere lower. This flips the usual intuition. We tend to think of atoms as being built from stable particles that are stable in themselves, and to think of the atom's stability as inheriting from the stability of its constituents. That would work fine if we were only building things out of protons and electrons, which really are stable in isolation. But neutrons break that pattern. Their intrinsic instability is real. Left alone, they die. And yet nature builds most of the mass of the ordinary universe out of exactly these particles, and holds them stable indefinitely by embedding them in structures that leave them nowhere to go. That is a subtle inversion. The stability of the ordinary matter around you is not a story about the stability of its ingredients. It is a story about the stability of the arrangements. Isolated, most of the neutrons in your body would be gone in an hour. Arranged into carbon and oxygen and nitrogen and calcium and iron and everything else, they have been sitting quietly since long before the Earth existed. The particles came out of the same primordial soup. The forces are the same. What lasts is what happens to be sitting at the bottom of the local well. If you think about it long enough, this is a general principle that reaches far beyond neutrons. The stability of everything we see on every scale is a story about local energy minima. Water sits in a puddle at the bottom of a low spot in the ground, not because water molecules are intrinsically fond of that patch of ground, but because that patch of ground happens to be the lowest reachable point given the constraints. Take away the walls of the puddle and the water flows somewhere else. It is the arrangement, not the substance, that determines whether the water stays put. Neutrons in stable nuclei are the same story at a much more intimate scale. The nucleus is the puddle. The bottom of the valley of stability is the lowest reachable point, and the neutron, given no lower place to go, stays. There is a physicist's summary of all of this that we can now write down cleanly. A free neutron decays because the total mass energy of a free proton, a free electron, and a free antineutrino is slightly less than the mass energy of the free neutron. A bound neutron in an unstable nucleus decays for the same reason, adjusted for binding energies. That is, the total mass energy of the daughter nucleus plus the electron and antineutrino is less than the mass energy of the parent nucleus. When that difference is positive, decay happens, on a timescale set by the size of the difference and the strength of the weak interaction. A bound neutron in a stable nucleus does not decay, because the corresponding difference is negative. The daughter would sit at a higher total energy than the parent, and energy conservation forbids the transition entirely. Same particle, same force, different arithmetic, different fate. There is one last piece of the picture that ties everything together, and that is worth naming even briefly. When we described the free neutron and its decay, we said that quantum mechanics offers a small probability per unit time for the decay to occur, and that the memoryless statistics of quantum decay guarantee that the process will eventually happen. That statement was correct as far as it went, but there is a subtle refinement we can now add. What we should really say is that quantum mechanics offers a small probability per unit time for the transition to occur, provided there is a valid, energy-allowed, final state to transition into. If no such final state exists, the probability is not merely small, it is exactly zero. The quantum event does not just take a very long time to occur, it cannot occur. There is no wave function overlap between the initial state and any legal final state, because no legal final state exists. The neutron does not sit there rolling dice forever with astronomical odds against decay. It sits there with the dice quietly put away. That is why the neutron in carbon-12 or oxygen-16 or iron-56 does not just live a very long time. It lives forever, at least as far as anything we can measure. There is no clock ticking down slowly. There is no roulette wheel spinning at glacial speed. The mechanism is not available at all. The weak interaction is present, ready to fire, exactly as much as it is in any other neutron. But the transition it would carry out, if it fired, would land the system at a higher total energy than where it started, and quantum mechanics does not allow such a transition to occur spontaneously in a quiet vacuum. The door is not just heavy, there is no door. This might all sound like an academic detail, but it has enormous consequences. It is the reason ordinary matter exists at all in the long term. If nuclear binding energy did not close the door on neutron decay for the stable isotopes, every atom in your body would be steadily losing neutrons on a timescale of minutes. Carbon in your bones would decay into nitrogen. Oxygen in your lungs would decay into fluorine. Everything would change composition, and nothing chemical would work the way it does, because chemistry depends on the identities of atoms staying fixed on very long timescales. The stability of the periodic table, the fact that carbon stays carbon and oxygen stays oxygen, is a direct consequence of the arithmetic we have just walked through. The universe is chemically knowable because neutrons in the stable isotopes have no lower energy state to reach. And it is worth pausing to notice how narrow the margin actually is. The free neutron beats its potential decay products in mass energy by less than 1 part in 1,000. The binding energy shifts that flip that margin from positive to negative are, on nuclear scales, quite small. If the strong nuclear force had been slightly weaker or slightly stronger, the binding energy landscape would have looked different, and the boundary between stable and unstable isotopes would have moved. Different elements would have been stable, different chemistry would have been possible, different stars would have burned. It is entirely reasonable, and mostly unprovable, to imagine that the whole shape of the observable universe hinges on quantities that could have been slightly different and were not. But in the universe we do have, the quantities are what they are. The free neutron loses to the sum of a free proton, a free electron, and a free antineutrino by about 782,000 electron volts. Nuclear binding energies rearrange that competition inside nuclei, sometimes in favor of decay, sometimes against, sometimes exactly on the border. Wherever it goes against decay, we find stable isotopes filled with quiet neutrons. Wherever it goes in favor, we find unstable isotopes whose neutrons eventually convert. And the whole periodic table of stable elements, the entire chemical foundation of the world we live in, is the collection of nuclei for which the arithmetic came out one way rather than the other. The neutron itself, throughout all of this, is the same particle, never anything else. Same quark content, same mass, same weak coupling. In empty space, it dies in minutes because it can. In a stable nucleus, it lives forever because it cannot. Nothing about the particle has changed. Everything about the accessible destinations has. And that, finally, is the answer to the paradox we opened with. The neutron is not obeying different rules in different environments. It is obeying exactly the same rules. But the environment decides whether those rules leave any door open, and in most of the ordinary matter around you, and the ordinary matter that you are made of, they simply do not. The next time you look at your hand, remember what is going on inside every atom of it. Neutrons that are, in themselves, intrinsically unstable, held quietly in place by the shape of the energy landscape their nuclei have found. Weak interactions constantly present, but forbidden from acting, because acting would take the system somewhere it is not allowed to go. The whole solid, familiar, chemically reliable world you inhabit is a consequence of that quiet arithmetic, played out silently in every nucleus around you, for as long as matter has existed, and for as long as it will continue to. The free neutron dies because it can. The bound neutron survives because there is nowhere lower for the whole system to fall. Same particle, same forces, same universe. Different books.